Alright, boys and girls, welcome to our very first video lesson in Chapter 11. Chapter 11, we will now begin our quest to discover calculus, and our first lesson is on limits. Limits. L-I-M-I-T-S. Limits. Let's go. Okay, a limit is defined as the value of a function as the function approaches a certain number in the domain. As x approaches a certain number, we'll call that c. As we get closer and closer, like almost infinitely closer, not quite getting there, as we get closer and closer to c, what is the value of the function? Let me write one here for you. So if f of x equals 2x plus 1, what is the limit as x approaches 3? Well, we can actually perform what we call direct substitution right here. As x gets closer and closer to 3, like 2.9 or 2.99 or 2.99999 or 3.01 or 3.0001 or 3.00001, what is the value of the function? Well, as x gets really close to 3, all we can do now is replace x with 3, and we now know we have 2 times 3, which is 6, plus 1, which is 7. So the limit of f of x as x approaches 3 is 7. So in other words, in this case, our c was 3 as x approached 3, and our limit was equal to 7, because as our function approached 3, not quite getting to 3, but becoming very, very close to 3, our function, as it gets very, very close to 3, is getting very, very close to 7. And you're probably asking, well, why do we need to take a limit? Why not just plug in the 3? Because sometimes we can't plug in the 3, and we will talk about those cases. There's also 3 cases when limits don't exist. The first one is if the function approaches a different value from the negative side, from the left side, or from the positive side, from the right side. If they approach different values, then the limit does not exist. The limit does not exist if the value of the function approaches infinity, either positive or negative. We just call that approaching infinity, or getting infinitely large or infinitely small on the negative side. So the value of the limit really technically does not exist as it approaches infinity. And we'll see this one in the vid. If the value of the function is going to oscillate between different values as we get closer and closer to x, or closer and closer to c, to our limit. And we will go over all these in class, okay? But this is not as hard as it appears. Okay, so we look at this first one. Our first method for evaluating a limit is called direct substitution. All we're going to do now is plug in the value of our limit, or our value of x, as we approach the value c. So in this case, our c is 2. What is the value of this function as we get closer and closer to 2? Well, there's no reason why we can't just plug in 2 to here, so we're going to directly substitute. Okay, so as I said, there's no reason why we just can't plug in 2, so the limit of this function as x approaches 2 is going to just be 3 times, let's directly substitute our 2 in there. 3 times 2 plus 2. 3 times 2 is 6 plus 2. So our limit is 8. Okay, let's look at this guy right here. We're going to do evaluate our second limit. This is method 1A, or it's really method 2. I don't know why we call it 1A. It's method 1A or method 2. We're going to use the table or the graphing feature on our calculator. Let's look at the function e to the x minus 1 over x, and let's figure out the limit as x gets closer and closer to 0. If I try to directly substitute now, I get e to the 0, which is 1, minus 1 up top. On the bottom, as x goes to 0, I'm going to get 0. Notice I have 0 over 0. That's not a defined term. In fact, that's called what we call one of our defined terms. So let's figure out what the limit is as x gets closer and closer to 0. Okay, so whip out your graphing utilities and type in e to the x minus 1 all over x and hit the graph. You should get this graph right here. But in looking at the graph, as x gets closer and closer to 0 from the negative side, it looks like the value of our function gets closer and closer to 1. As x goes to 0 from the positive side, from the right side, it looks like we're getting smaller, 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 and it's going to 1. Okay, so it looks like our limit is 1 by looking at the graph. Okay, if you look at the table now, when x equals 0, sure enough, we do have error, but getting closer and closer to 0 from the negative side, the value of our function when x is negative 0.3 is 0.86. The value of our function is negative 0.2. The value of x is negative 0.2. The value of our function is 0.906. And as x goes to negative 0.1, we're getting closer to 1, it's 0.95. Again, we have error. As we move closer to 0 from the positive side, when x is 0.3, we have 1.16. When x is 0.2, we have 1.107. And when x is 0.1, we have 1.05. So again, it looks like we're getting closer and closer to the value of 1. So the limit as x goes to 0 is 1. 1. 1. 1. Okay, let's look at this function. Find the limit as x goes to 0 of the function f of x equals cosine of 1 over x. Okay, if I directly substitute, if I let x be 0, I'm going to get in my function cosine of 1 over 0, which of course we know 1 over 0 is undefined. That's infinitely large, so we don't know what that is. So let's figure out what's happening. Go ahead and whip out your graphing utilities and put this into your calc right now and hit the graph. In the standard in a Zoom 6 or the standard viewing window, you get something that looks like this. It's kind of hard to tell what's going on there. Maybe our function is going towards -1. It kind of looks like that. But let's zoom in. So go ahead and zoom in once. You should get that on your calc now. What's going on? It's hard to tell. It looks like that the value of the function is starting to bounce around. We don't know what's going on. So let's zoom in one more time. And now when I zoom in one more time, I can see that sure enough, as x gets closer and closer to 0, in other words, as I move from the negative side on my function starts to bounce up and down until we get to 0. I'm not sure what happens there. When I move towards x equals 0 from the right side, as x gets closer and closer to 0 from the right side, we can see now that, again, my function bounces around, and I don't know what's happening here, so the graph is inconclusive. Let's look at the table. Sure enough, we see that when x is 0, we get an error. The function does not exist at 0. But more importantly now, what's happening to the values of our y as x gets closer and closer to 0? We're bouncing around. In fact, if you change your table and you count it by, say, 0.01s, you would see that our function is going to bounce up around. So therefore, this limit does not exist because our function is oscillating between values. It's oscillating from -1 to 1 as x gets closer and closer to 0. Okay, so looking at this guy right here, we have f of x equals sine of pi x. We're finding the limit as x gets closer and closer to 1, which is going to be right here on our graph. Looking at our graph now, it looks like that our function approaches 0 as we get closer and closer to 1 from the negative side. Our function approaches 0 as x goes to 1 from the positive side. Looking at our table right here, we see now that as x gets closer and closer to 1 from the negative side, so 0.7, 0.8, 0.9, we go from 0.80 to 0.58 to 0.30, getting closer to 0. When x gets closer and closer to 1 from the positive side, from the right side, we get -0.8, -0.5, negative 0.3. It looks like we're getting closer and closer to 0. And sure enough, by direct substitution, we can see now that when x is 1, our function is equal to 0. Okay? So in other words, the function was let f of x equal sine of pi x. Well, when x is 1, we get our function is equal to sine of pi, which is sine of 180, and if you remember, that is 0. So sure enough, our limit equals 0, right here, 0. Okay, a couple properties of limits you need to know. This is not hard. Just whatever you can do with a real number, you can do with a limit. In other words, you can multiply a limit by a scalar. So the limit of a function, when I multiply the function by b, is just b times the limit. If I add limits, the limits are going to be the addition or the subtraction. I can multiply limits, I can divide limits, and I can raise limits to a power. Let's see what that means right here. So if I look at this problem right now, I got f of x is equal to x over 4. I got g of x is equal to the square root of x squared plus 5 over 2x squared. I want to find the limit as x approaches 2. Well, the limit as f of x as x goes to 2, so limit, so the limit of f of x as x goes to 2 is going to be 2 to the 4th by direct substitution, which is 16. And the limit of g of x was 2 here, as x goes to 2, is equal to the square root of 2 squared, which is 4, plus 5, over 2x squared, which is 2 times 4, which is 8. So it looks like this is going to be, let's see, square root of 9 over 8, which is 3/8. So the limit of f of x as x goes to 2 is 16. That's this guy. And the limit of g of x as x goes to 2 is 3/8. So now we can look at this. What would what would the limit of f of x be? Well, the limit of that is 16. As we look at b, the limit of g of x, we just said, was 3/8. What is the limit of their products? Well, it's 16 times 3/8, which is, I can cancel. So it's 16 times 3/8. I can cancel the 8 with the 16 and get 2. So that is equal to 6. And lastly, d. What is the difference of their limits? Well, it's 3/8 minus 16, which is, I'm going to write this down here at the bottom in red, negative 15 and 5/8. All right. Hey, that's it. Have a great day, folks. We shall see you soon.